they've given us over the years. Today, they have invited Sebastian Mueller from Biognosys to give this talk that I think will highlight their technology. Sebastian, as I say, is from Biognosys, a Swiss company, and he will be talking about plasma proteomics in a kit, targeted proteomics on the discovery scale. So just to reiterate that, Sebastian is from Biognosys, speaking on behalf of Thermo to all of us today on the subject of targeted plasma proteomics. And before I turn it over, I'll just remind everyone there is time for Q&A. Please use the Q&A function down there in your Zoom screen. And I'll turn it over to Sebastian. Tell us about it.
Thank you, Dave, for the kind introduction. And I also want to thank the organizers for putting together this great online gathering. I'm really happy to be part of it, especially in these times. And especially thanks to Thermo Fisher for giving this opportunity to talk about our latest results with SureQuant and PQ500 in this seminar. And what I'm going to present to you is entitled The Plasma Proteome in a Kit, Targeted Proteomics on a Discovery Scale. So what I want to talk about today is first, I'll give a general introduction to discovery plasma proteomics and the challenges associated with it. And then I'm going to explain how the SureQuant methodology actually works. Then we used it on a small case study of a small cancer patient cohort where we got the plasma samples. And then I will wrap up with an outlook we're still going to do and some conclusions. So first, what is the human plasma proteome? The plasma proteome consists half of blood cells, half of plasma. Plasma is actually the liquid part of the blood and is containing mostly water, only 7% proteins, and other important small molecules like vitamins and electrolytes. The good thing about plasma is it flows through basically all parts of the human body, so it's very well suited to investigate the human health state. And moreover, it's very easily accessible with just a pinch, and usually the samples amount you get from plasma are really not limiting, so you get basically a ton of proteins, nothing like compared to other biopsies or pack-sorted cells. But what is a bit problematic with plasma is that it has a really high dynamic range, and that gets challenging for many analytical techniques. Before I further dive into this point, I want to introduce something to actually look at your plasma workflow, and something we found very useful is that you compare the proteins you identify and quantify towards an inventory of plasma proteins with known concentration ranges in the population. That can be from any source, any assay, any proteomic assay, basically. And for a long time, we used this seminal paper from Anderson back from 2002, where he presented population quantities of plasma proteins for actually 70 entries. And for the longest time, we were using this to check when assay how deep, which is kind of the lowest protein we can quantify and what is the nominal range that it's supposed to be in the population. Luckily, last year, there was a new paper by Matthias Ullén and the Human Protein Atlas lab, and they assembled the human secretome. And in this publication, they actually did a new literature research, and now they extended this list where they figured out the normal concentration ranges for more than 365 protein entries. So the general distribution does not really change. We still have the classical plasma proteins pretty high up, and then some mixed functions in the middle, which come from tissue leak, and other functions, and then the hormones and interleukins basically very, very low down. And we're going to use this as reference to see where we are with our plasma workflow. So back to the original question. So why is this large dynamic range challenging for discovery proteomics in plasma? And we start out with a simple Orbitrap scan, and this has a very limited dynamic range. So with a single Orbitrap scan, you could not detect much of the human plasma. Obviously, nobody is doing this, so we have developed techniques like LC separation and trapping to largely extend this dynamic range. And I've shown here a representative DIA study, which actually we put out last year. It's a capillary flow DIA, but there are numerous studies in DIA and DDA, which basically all end up in this ballpark numbers that you in the top half of plasma protein amount. So why is this the case? What is the limiting factor here? It's that these high abundant plasma proteins actually yield a lot of peptides when you digest them with trypsin, and you need to analyze them by DDA. You trigger each one of these peptides, and when you go down, you will trigger more from the high abundant ones before you reach the low abundant ones. In DIA, it's not so much the problem that you trigger them, but these peptides are still there, and actually there they can fill up your trap in your predefined MS2 isolation windows. So you basically don't have the space to analyze the lower abundant ones. So how could we help with this? And we thought about, let's look at targeted proteomic approaches, where you basically analyze only a predefined set of targets, and you don't care that albumin is yielding hundreds of peptides. You just analyze one and then go on to peptides from other targets. And 2 years ago, we launched a set of reference peptides, because the gold standard in target proteomics is still quantification of a heavy spike-in standard and then quantifying the endogenous peptide against the spike-in standards. And we called it PQ500 because it covers more than 500 human plasma proteins. In total, it's a mixture of more than 800 stable isotope standard peptides. And the way we developed this was actually experimental. So we used a pool of plasma from multiple diseases, which we digested in multiple conditions. So favorable digestion conditions, but also adding some non-favorable digestion conditions. And then we fractionated this first offline, and then we also fractionated this during the MS acquisition, so gas phase fractionation, to get a really comprehensive set. And there we got a catalog of peptides, which we then selected based on the robust cryptic release, the stability in solution, and based on a scoring scheme, other criteria. We also excluded several peptides on purpose, like for immunoglobulin variable proteins, where there are a lot of entries actually in UniProt, but they're not really helpful because only a small part of an antibody, and you cannot really follow up these hits when you get them. So then when we use this comprehensive set of reference peptides, we started using it in a PRM acquisition scheme, scheduling all the 800 heavy peptides and the 800 lights. And we found that we actually really can increase our coverage of the plasma proteome, dig a bit deeper in. But we also found that it's quite difficult to perform this analysis, because to schedule this high amount of targets, we actually had to push the limits of our calibration and use a nonlinear gradient and the nonlinear calibration using all heavy peptides as data points, and then use also very narrow scheduling windows of less than 5% of the gradient, and even then end up with a middle-sized cycle time. And with this narrow scheduling windows, there's also the danger of really missing the peaks if the LC performance is varying, and especially for nano LCs, this is constantly happening. Additionally, when we looked at the data, we found that even with this very narrow scheduling approach, it's still not very efficient, because the peak boundaries is less than a minute, and we're still scheduling for maybe 4 minutes. So we record a lot of data, which we don't use. And even if we look at this heavy and light peak, and on the right, you can see the plots of the fill time here for the light and here for the heavy. See that the light nicely uses all the time it can for the trapping, but on the heavy, which is nicely and easily detectable, we do not use our time efficiently. So we waste a lot of time by not filling the trap. And that was basically the point when SureQuant became available. So SureQuant is an implementation of internal standard trigger PRM, ESPRM, what you might have heard in earlier times. And it became available at ASMS last year on the Thermo Scientific Orbitrap Fusion platform and the Explorers 480 in the stream. SureQuant essentially is kind of a mixed workflow. So it is data dependent, because it's relying on the heavy peptides, cis peptides, but it's a targeted workflow. And there's no scheduling required at all. So basically, if you look, this is PQ500 alone run, and this is PQ500 plasma, it basically looks for the peaks and then uses this as reference where to trigger the endogenous light. I'll explain in more detail in a minute. SureQuant can be used with basically any set of heavy peptides, but on the Thermo instruments, there is several kits are pre-programmed, like our PQ500 kit, which can be nearly used out of the box. So how does SureQuant work? So basically, when you select in the tune the PQ500 method, SureQuant method, and run it, the data you get looks pretty much like you used to for plasma, but under the hood, there are a lot of things happening. So after every MS1 scan, the MS1 scan is the survey scan, the instrument automatically looks for the heavy peptide, so for the mass over charge of the heavy peptides it has in this list. So at this point, the target peptide is completely ignored. And if that M over Z value is above a certain threshold, it will go to the next. And here at this MS1 trigger threshold, this is actually one value that can be refined in the method based on your LC to check how high are the intensities of the heavy peptides on your specific setup. So that's why nearly out of the box is one thing you can do. Once this is done, and the instrument finds a heavy peptide, it triggers an MS2 scan for that heavy peptide at a low resolution. In this fragmentation pattern of that MS2 scan, it checks by a fragment ion matching, a simple one, if it finds the fragment ions that are associated with the heavy peptide it thinks that is, and this it's positive, only then a scan is triggered for the endogenous target peptide, which is known due to its offset to the heavy, and then you can trigger a high quality MS scan of a high resolution of that target peptide. And compared to the things I told you a bit earlier, that this advantages in several aspects. So for one, these scans for the heavy are at low resolution, but we know the heavies are also easily detectable, and this is very fast, so you can do this several times without increasing the cycle time a lot. The acquisition of the target peptide is at higher resolution, so it has an increased sensitivity, but it's also very selective, so it does not happen a lot because it has all the gatekeepers beforehand. How does the data analysis look of SureQuant data? So as a novel workflow, it provides some challenges actually. So SureQuant by itself is actually a peak-centric acquisition like DDA. So the peak it finds in the beginning, it will carry through all these different steps. And other targeted methods like MRM or PRM are usually panel-centric. So in PRM, when you schedule 800 peptides, you will get a mass spec run with 800 MS2 windows. In SureQuant, you will still get a mass spec run with 50,000 different MS2 windows because the isolation will be set around the peak it actually finds and not the theoretical peak. Also, because of this strategy it uses, especially in complex panels like PQ500, the triggering of the endogenous peptides can be a bit late and lead to peaks that are not fully captured in the acquisition technique. So this is not a very common event. This is more of a rare event. So we see it in about 10% of the peaks maybe, but it is something we have to deal with when we analyze this data. At this point, we also wanted to get to an automated data analysis platform. That's why I want to quickly introduce you to SpectroDive, which is our software for easy scheduling and analysis of target acquisition methods. You already have seen a glimpse of it when I showed you the PRM scheduling, which we have included in SpectroDive as well. So usually what SpectroDive would do when it analyzes data, it can read directly the raw data of MRM and PRM runs. It would do then an automatic mass and IRT calibration. It would then perform peak picking, which on PRM we do in MS1 and MS2. Obviously in MRM we only have our MS2 values, and we perform scoring on both. And after we've collected all our scores, we have an automatic FDR control, which finalizes our identification. For SureQuant analysis, we actually had to adapt this workflow in several aspects. For one, as I've shown you that the SureQuant raw data actually looks a bit different than PRM and MRM data, so we had to adjust how we handle the SureQuant data. Next step is pretty much the same. We still do the dynamic calibration, but the peak picking, we actually now split into two parts. We do a normal peak picking based on our heavy spike in peptide. And then for the quantification, we refine the peak picking to an area where we really have a signal in the heavy and the light. So we narrow the window to really get an accurate quantification. Afterwards follows our FDR control, and then we get our quantification values out. So after all this intro, I want to show you the results we get actually with this in our case study. So for this, we used a commercially available plasma cohort, which consists of a healthy control group and then a mixture of cancer types. In total, we have 3 different cancer types, which we mass together as one cancer group of fairly old patients. The plasma samples we processed in a normal way for mass spectrometry with a triptych digest. We do this in a high throughput fashion in 96 well format, not with a robot yet, but the next thing, the best thing next to it. and then we spike in our PQ500 reference peptides right before the acquisition. Then we use the SureQuant acquisition strategy on the Explorers 480. In this case, actually, we used really the out-of-the-box method. So it's just going into the tune file, selecting the method, and pressing start. So it's pretty much the same as you would do with any DDA or DA method. There's no additional things to do. We use the nanoflow acquisition, in this case, a 60-minute nonlinear gradient, which gives us a throughput of about 18 samples per day. And of course, we acquired it in randomized fashion. As I explained earlier, the data analysis is done in SpectroDive, where we do all the peptide data extraction, protein quantification, also the statistical analysis right in the tool. So how does the data look with these acquisitions? The peptide IDs, in this case, of course, limited by the amount of reference peptides, but also the protein IDs, we get a consistent identification of more than 500 proteins in each of the samples. There is quite a bit biological variation because we only have 409 proteins in total that we get in all of the samples. We also did triplicate injections of both groups, actually also of both cancer types, the pancreatic and the lung cancer, to assess the quantitative CDs from the method. And there you see they are between 7 and 9%, which is a little bit higher than what we're used to when we use spike and targeted methods, but it's still way below the biological variance which we find in both groups. In the cancers, of course, increased because we have different cancer types in this case. Do the quantifications we get make sense? So yeah, so we do get several candidates which we find upregulated in the plasma of the cancer patients. And as an example of the C-reactive protein, I want to walk you through how we actually end up with this quantity. So we start out with a single peptide quantity in a single run. There you can see how we perform the peak picking and peak refinement, and also for the target to reference ratio, we only use this narrow area where we really have data in both. Then we can directly calculate an absolute amount. And that we do basically in every run. Here in this overview, you can already see that it looks like this one is enriched in the cancer group. Then we look for the candidates and give the candidate overview. In the PQ500 panel, we actually have 3 different peptides for the C-reactive protein, but they all behave very similar. Here, actually in white, you can see the triplicate injections we did, which are not part of the statistical analysis. And what you also can see that really, despite that there's a lot of biological variation in this data set, we can nicely retrieve a significant regulation of C-reactive protein in the cancer group. And when we look at overall the candidates we identify in this small study, we can see that according to literature, they are very relevant for the host response to a tumor. So there's all the different S100 proteins. We have complement as innate immune response, and the acute phase proteins like C-reactive protein, as I've shown you just. So that already brings me to an outlook. So we use this method very much out of the box. The topic of this presentation was a turnkey plasma solution. But can it actually be improved further? And yes, it can. So one step actually, which we did not do for the study, was to really optimize the trigger intensities to our setup. So we really used the trigger intensities as set up in the thermo method, which worked very well, because probably we use a very similar chromatography. But we are also working to implement this in SpectroDive that you can do easily a survey run. The survey run functionality is in the tune. Thermo, you can do this, and it's basically a DDA run with an inclusion list of all heavy peptides that really makes sure that you identify all your heavy peptides, and then you can quantify them on your system, and then set your threshold of intensity, usually 1% the peak intensity, and then update your trigger list intensities. One other thing we were looking at, so we used this rather short gradient, and we know that it's a PRM-like method, so it's also SureQuant has a cycle time, and it likes that its cycle time is shorter to get a more accurate quantification. And to test this, we actually used the pool of the cancer plasma samples, and also did the SureQuant acquisition as it is pre-programmed, and used it on 60-minute and 120-minute gradient. And what we can see here in these results is that the proteins we quantify in these 2 gradient lengths that are overall quantified are actually not very different. They're very much the same. but that the assays with a low CV is below 20% or even below 10% dramatically increases when we increase the gradient length. And also the median CV really goes down when we increase the gradient length. So this can be really helpful if you have the time to spend more time on the acquisition of your samples. Where we also see a good application of this workflow is in multi-site or continuous plasma studies. So basically, multi-site means that you have several MS instruments where you want to split the acquisition of a cohort, and then both instruments might have a different baseline. Or a long continuous study where you get one cohort in one time, and then samples are added, and then you measure a second cohort, and then you measure a third, and the mass spec evolves with maintenance and replacement parts. Then you also have different baselines and how this can look. And this is actually not data acquired with SureQuant, but we did in a previous study with PQ500 that we found that over this, when you continuously acquire, the instrument sometimes is in a different state, and then you cannot directly compare your label-free data, but the spike-in derived absolute amounts are definitely on the same scale, so you can directly compare the protein amounts you get out. And this brings me to the conclusions, where I can summarize what I just showed you. So the first thing is that the SureQuant acquisition with the pre-programmed PQ500 method is really a turnkey solution for plasma proteomics. In the concept I've shown you earlier, how deep can we reach into the plasma proteome? At this point, PQ500 in combination with SureQuant really gives us the most sensitive method for single-shot plasma analysis at this moment. And it works. It's very easily to set up and to execute at this point. The data analysis can be facilitated with the pipeline we introduced in SpectroDive. So there you can automatically analyze your SureQuant runs with the parameters I've shown you. It works pretty well. You don't need much manual input. In this proof of concept study I've shown you, we actually could quantify more than 500 plasma proteins in each sample, and we could identify biological relevant candidates. It was a very small study, and we surely need to test it on a bigger cohort and see how it performed there. And also lastly, that this methodology of SureQuant is just a starting point basically, and it is really possible to develop it to your individual needs more depending on your throughput needs and your sensitivity needs. And with this, I would like to thank the people who were involved on the diagnosis side. It's Tejas, who's the main developer for SpectroDive and put all the SureQuant functionality in. Jan is working actually on optimizing the SureQuant workflow, and Lucas is guiding us through this endeavors. On the Thermo Fisher side, I would like to thank Sebastian Mueller, with which he had a lot of contact from the beginning, also Shannon Eliuk and Emily Chen. And also special thanks to Julian Saba and Sally Webb for giving me this opportunity to present this data here in the webinar. And now I'm happy to take your questions.
Great. Thank you, Sebastian. That was wonderful. I do have a number of questions here in the list. I'll start, since we heard the wonders of TMT just a little while ago from Professor Gigi. The question was asked, how do you compare this with, for example, TMT and things like CVs or missing values, and how depth you could go, mass spectrometry time, for example?
I think, so the biggest difference is that with plasma, we really would like to go into large sample sets. So when we really think of hundreds or even thousands of samples, so TMT at some point becomes not really feasible anymore. So you would need to run so many different plexes that it's not feasible. On a small set of samples, so we've seen the overall data completeness we got with the SureQuant method was nice. It was probably not as, so in the lower plasma protein range, there are some missing values, which in this case might also be due to the biology. So I cannot rule that out. But overall, the first impression looked very nice. So if you can detect it in your sample, it looks like SureQuant is able to give you actual quant value out of it.
Okay, thank you. There's another question which you may have answered along the way, but it did come up, so I'll ask. So when you're working at low microgram samples, what's your go-to peptide fractionation strategy?
That's also like with plasma, we don't have this problem luckily, so we're also more in the milligram range of protein. But for the development, so we usually go to high pH reversed phase C18 to fractionate. It also for the development project we use this and find that working pretty well.
All right. So again, towards the end, you addressed a little bit the depth of the plasma proteome. Do you think there are limits on how far you could go? Is there a next step that you're aiming for? You know, just how deep do you think we can aspire to?
Yeah, that's actually a very good question. So there, of course, at some point there are limits to add amount of heavy peptides to a sample. So at this point, we are not really there yet. We believe we can extend this definitely beyond the 1,000 proteins, 1,000 peptides. If you go one by one on protein, maybe even a bit more. But then at some point, we'll have more heavy peptides in plasma sample. And one thing that is also really determining our sensitivity is to get the sample on the column to be able to analyze it. So I think there will be limits. And so 5,000 proteins, that's probably not, but we're not there yet.
Okay, we had a simple technical question here. Can we set up PQ500 on Orbitrap Fusion?
Yeah, so the SureQuant, as I've shown you, is in the Orbitrap Fusion platform and its Explorers platform in the latest versions of the tune. So if you're not seeing it, you should update your tune. Then it should be there.
So maybe the same answer, but a related question was, can you use the SureQuant acquisition in the QEHF?
No, that is not possible. So it's really, at the moment, limited to these platforms, the Fusion platform and the Explorers.
Okay, so we have a question here that I think is a really good one. It's about experimental design, and have you considered applying the approach in a paired test survey design? And I'd extend that to, how should we really be doing plasma proteomics? Does it make sense to compare, many different people, or is it better to look at a longitudinal study of the same person across multiple time points?
So I think both has its own value. So if you compare a lot of people, it's on large cohorts, you might get general biomarkers. The problem we actually have is, so also what we found is that a lot of these plasma proteins have quite a difference between individuals. So when you look at a population, you kind of average this out, but that might make it different to see subtle changes. So it's good to find general biomarkers, but if you profile a single person over time, you might see a small change because you really know this person's level of protein X very well. And once this changes, you're sensitive to this change, while over a population, this might be masked as overshift. So I see both as value. In the long term, it would be nice to profile people longitudinal.
Okay, so we have a question here about single peptide quantification versus multi-peptide quantification. I think that is, rolling up to the protein level. What are your thoughts there? Do we trust one peptide?
Yeah, so actually we are still, this is also a very excellent question, and as we acquire more data, we are continuously looking into this, and don't have a final answer yet. But what I think now is that for this spike-in, actually, a single good peptide really gives you a good quantitative value. So why do we have then more than one peptide is that not in all conditions, maybe that one peptide is available. And also in everyone has a different processing platform, each has a different contaminations in their systems. That's why for the more important proteins, we have more peptides, but you should get basically an accurate quantification from the single peptide across your samples.
Okay, so we have a question on sample preparation, and it sounds like just the practicalities, how challenging and critical is prepping for large-scale P500 quant kit?
So the sample preparation for plasma is, in general, is not so challenging. There are a bunch of, so we have a kit, a 96-well kit, but there are also other sample preparation kits out there which you can do this. What is really important is that you randomize your samples accordingly, that you don't prep all from one condition once or in 196 well played or this, that you really make a proper experimental setup before you start pipetting. And I think then it goes straight through. Also, the cleanup of plasma samples is very important. Otherwise, your nano LC won't last long if you want to do it on nano. But that would be my takes on this.
Okay, so this is a related question came up with a note that the PQ500 is added right before injection. So do you do anything to control for sample processing to normalize the data?
So no, there we don't. What we find is the easiest workflow is to basically to keep the plasma volumes for each sample constant throughout the processing workflow and then also for the injection. So that's why you can basically right away calculate back on the protein amounts in your original plasma sample, and each sample should have the same loss. So for the relative analysis within your sample set to get maybe a biomarker study to get your biomarkers out, we can ignore that loss because it should be similar in all samples.
Okay, so a question came up about low and high resolution. Could you clarify, in the method is, the light done at low resolution and the heavy at high resolution, and how does that affect the quantitative accuracy?
So yeah, so in this case, in the standard setup, the heavy is done in 17.5K resolution and the light is done in 60K resolution. And also we compared this actually to our normal PRM data where we have both channels in the same resolution. And so far we could not see any quantification bias. So anything that the heavy channel would be underrepresented or less accurate. A consequence, so why is this probably the case, is that the peptides we spike in have a very balanced intensity across the whole gradient. So we can basically nicely detect all the heavies with this low resolution throughout the gradient.
Okay. We may have touched on this already. SureQuant in the Fusion Lumos instruments, does that require a tune upgrade or is that just going to work out of the box?
So I'm not 100% familiar with all the different versions of the tune of the Fusion, but definitely in the latest versions it's in. So all versions past last ASMS, they should have it. And the Fusion is otherwise very well suited to do this workflow.
All right. Next question is, can SpectroDive process survey run data in the case where the user wants to adjust the intensity thresholds for the final SureQuant method?
So we are actively working on this one. So it will be part of the next SpectroDive release, which you can expect in the middle of this year. And there we will have a strategy to do this. Okay. The current version of SpectroDive does not have it yet in.
Okay. And question comes up, is there advantage to using SureQuant compared to straightforward DIA with the PQ500 spiked in?
So as I've shown you in this last graph, so the data we got is quite a bit, so we deeper in the plasma proteome we get with the SureQuant method compared to the DIA method with PQ500 spike. And the main reason for this is that we really spend more time on the actual endogenous peptides that corresponding to the heavy peptides in the SureQuant method. Basically the added benefit you would get with the DIA method with PQ500 spiked in, that you would get the PQ500 proteins and peptides, but additionally you would also detect all other label-free peptides if you want to look at those.
Okay. There's a question about increasing throughput on the LC methods. Are there other technologies like EvoSeps, which is interesting. We will hear from EvoSep shortly. But is there a way to speed up the LC part?
Yeah, so I've shown this in the outlook. So it can be definitely beneficial to increase the gradient length to basically give the method more time to go across the peaks to get more data points per peak. One thing about the SureQuant method, it's quite strictly pre-programmed. So the way the instrument distributes the low resolution heavy scans and the high resolution light scans is all set. And that makes it a bit hard to predict how a shortening of the gradient length will further look. So I would really like to try this out, but at this point, I cannot really predict how the data look.
Okay, so another platform question. Have you compared your method to the SomaLogic platform? And if so, what are the advantages?
So to be honest, I didn't. So far, we could not have the same sample measured here and there. I can only say the advantages we have here, without saying much about SomaLogic, is that here we can really look at the data. So there is a way that you can manually validate what you're seeing. So even if you would see an outlier, you can look at the ion traces, you can see how it looks. Is there a contamination? Is there another transition that's going in? So why does it look good or why does it look bad? So that's definitely nice about this data we have here. And I'm not aware that this is also possible with the SomaLogic data.
So here's an interesting question. Is PQ500 compatible with the Tomahawk method, which is also a data-driven sampling method that was originally for, where it was designed for use with TMT. That's an interesting question. How you might.
It's an interesting question. I would have to think about that. So I cannot give you really an ad hoc answer. But yeah,
okay.
True.
Well, so here's a sample or a question whether your data have given you any insights and to why plasma tends to show so many missed cleavages compared to cell lysate digests. I mean, is that your experience too? And do you know why?
Yeah, so that's a very interesting question, and we have also looked at this a bit, and it's interesting that especially the amount of KP and RPs you find in plasma is very high, and trypsin really in the plasma samples doesn't seem to cleave there. So I would not really consider these a miscleavage in plasma samples. And if you take this out, then the amount drops to more normal levels. But in total, I do not have an answer for this. Maybe there's some residual antitrypsin activity in plasma, maybe more or less in certain samples, if it's not fully denatured. But yeah.
Okay, so I just see two more questions here, and we're still on time, so that's great. Is it possible to analyze SureQuant data with SpectraNaut, or is it only with SpectraDive?
No, at this point it's only in SpectraDive, and this is so we have specifically implemented this pipeline. So we, as I mentioned, we need to have a bit of a separate processing of the data for the SureQuant data, and right now this is only SpectraDive.
Okay, and Ray, SomaLogic in this approach, can you see peptides with SNPs?
So when we created the panel, the PQ500 panel, we did not really look for peptides with SNPs. So at this point, we're limited in the panel we have at this point, and so I can say we don't look for this. We actually, there was we had done a study where we have seen in a certain subtype of samples that one peptide, where we have several for a protein, did not give a correlating result. And when we had a closer look and also compared to this label-free data, we actually found that one peptide has a SNP in a certain population type. So, but that was a discovery mostly by chance, I would say. So not systematically we look at SNPs with the kit. Okay.
Great. So we've come to the, I think, to the end of the questions. I've noticed in the chat that Shannon Eliuk has pointed out that SureQuant is supported in Orbitrap Tribrid Series 3.3 instrument control software and Orbitrap Explorer Series 1.1 SP1. So hopefully that answers some of the technical questions on what instruments are compatible. So that's great. So I'd like to thank Sebastian. I think we're a few minutes ahead of schedule. So I'll ask the other panelists, shall we go back to housekeeping slides for a couple of minutes or forward straight ahead to the next step?
We can go ahead.
Okay, great. Thank you.
All right, so I'm gonna join everyone else and congratulate Steve Gigi for a very well-deserved award. And also thanks Sebastian Mueller for a wonderful talk. And thanks Thermo for giving him the opportunity to give this talk. So we will continue now with our celebration of US HUPO awardees. And it gives me great pleasure to introduce to you Catherine Costa.